Hello chemistry students, Dr. Tellis here. This chapter we are focusing on nuclear chemistry. So much of inorganic chemistry focuses on the chemical reactions that take place with the electrons. But with nuclear chemistry, we are focusing on the nucleus of the atom. In this section, you will be able to identify alpha, beta, and gamma radiation, the three major types of radiation in natural radioactive decay. First, let's do a quick review of notations, mass number, and nucleotides. Mass number is the total number of protons and neutrons in a nucleus. A nucleotide is an atom characterized by a definite atomic number and mass number. Here is one way of notating sodium 23. That tells me that sodium, if I looked at my periodic table, it has an atomic number of 11. While it's not written in this notation, you can find it out simply by looking at its name. The 23 tells me its mass number. That is protons and neutrons. So to figure how many neutrons that has, you would just do 23 minus 11. In this kind of notation, we're given the symbol. The top number is the mass number. The bottom number is the atomic number. If you're ever not sure of the atomic number, look at the periodic table. Some more review. We have protons, neutrons, and electrons. Protons have a positive electrical charge. Its mass, 1.67 times 10 to the negative 24th grams, but the relative mass we say is 1 AMU. Neutrons, no electrical charge, have the same mass as a proton. Again, its relative mass is 1 AMU. Electrons have a negative electrical charge. Its mass is a lot smaller than a proton or a neutron. Its relative mass 0.0005 AMUs, so a fraction of a proton or neutron. If we were told sulfur-32, we would need to look at the periodic table to figure out how many protons sulfur has, and sulfur has 16 protons. This 32 tells me its mass, so 32 minus 16 tells me that it has 16 neutrons in that nucleus. It doesn't say anything about being a positive charge or a negative charge, so however many protons it has is how many electrons it has because it's neutral. Bromine 79, look at the periodic table. Bromine's atomic number is 35, so it has 35 protons. It doesn't say anything about being charged, so 35 protons is 35 electrons. And to find out how many neutrons it has, we take the atomic mass, 79, subtract 35, and we get 44 neutrons. The last piece to review would be the topic of isotopes. Isotopes are atoms of the same element, so they have the same number of protons, but they have different mass numbers, so that means they have a different number of neutrons. For example, boron 10 and boron 11. Both are borons, so both have 5 protons, but if I take 10 minus 5, I get 5 neutrons. 11 minus 5 gives me 6 neutrons. Here's another way to show that notation. That just tells me that boron 10 has 10 things in the nucleus. 5 protons, 5 neutrons. Boron 11 has 11 things in the nucleus. 5 protons, 6 neutrons. So this nucleus is heavier. Now, late in the 19th century, while studying radiation emanating from uranium and thorium, Ernest Rutherford stated, "There are present at least 2 distinct types of radiation, one that is readily absorbed, which will be termed for convenience alpha radiation, and the other a more penetrative character, which will be termed beta radiation." Subsequently, charge to mass ratio measurements showed that alpha radiation is composed of helium nuclei, and beta radiation is composed of electrons. A third type of radiation was later discovered by the French scientist Paul Villard. He named it gamma radiation, using the third letter in the Greek alphabet, in keeping with Rutherford's scheme. Unlike alpha and beta radiation, gamma radiation is not affected by electric and magnetic fields. Rather, it's a form of electromagnetic radiation like X-rays, but even more energetic. Alpha radiation can be symbolized either one of these 2 ways. Alpha radiation like this, with the symbol alpha, has 2 protons and 2 neutrons, which is similar to a helium nucleus. It is not a helium atom, though, because it does not have the electrons associated with it. We're just looking at the nucleus of a helium atom. Alpha decay can be shown like this. Uranium 235, so that's its mass, and protons has 92 protons. When it decays to thorium-231, notice that I have a mass difference of 4. So I have 4 as my mass on top, and I have a proton difference of 2. So that would be alpha decay. It could be written like this, or it could be written, instead of the helium, have that alpha symbol. Beta radiation can be shown using that beta symbol or showing that electron symbol. The mass is 0 for electron, and it's a -1 charge. Obviously not a 1 because that would show me that it was a proton. -1 has that electron. Beta decay could be shown like this. Uranium-235 and 92 protons. Over here, if I have 93 to neptunium, that means that I need an electron, because 93 minus 1 would give me 92. And notice that the mass stayed the same. So I would need the 0 mass of that electron. And gamma radiation, its symbol is this gamma symbol. It looks like kind of a cursive Y. It has no charge, no mass, because it is a form of electromagnetic radiation. So gamma decay would be shown like this. Here's our uranium-235 showing the decay. Notice that the mass stays the same, the atomic number stays the same, the element is the same. We show the gamma radiation given off with a 0 mass and the 0 charge. I want to give a quick video clip on how the phenomenon of radioactivity was discovered.
If you want a glimpse of Marie Curie's manuscripts, you'll have to sign a waiver and put on protective gear to shield yourself from radiation contamination. Madame Curie's remains, too, were interred in a lead-lined coffin, keeping the radiation that was the heart of her research, and likely the cause of her death, well contained. Growing up in Warsaw, in Russian-occupied Poland, the young Marie, originally named Maria Skłodowska, was a brilliant student, but she faced some challenging barriers. As a woman, she was barred from pursuing higher education, so, in an act of defiance, Marie enrolled in the Floating University, a secret institution that provided clandestine education to Polish youth. By saving money and working as a governess and tutor, she eventually was able to move to Paris to study at the reputed Sorbonne. There, Marie earned both a physics and mathematics degree, surviving largely on bread and tea and sometimes fainting from near starvation. In Paris, Marie met the physicist Pierre Curie, who shared his lab and his heart with her. But she longed to be back in Poland. Upon her return to Warsaw, though, she found that securing an academic position as a woman remained a challenge. All was not lost. Back in Paris, the lovelorn Pierre was waiting, and the pair quickly married and became a formidable scientific team. Another physicist's work sparked Marie Curie's interest. In 1896, Henri Becquerel discovered that uranium spontaneously emitted a mysterious X-ray-like radiation that could interact with photographic film. Curie soon found that the element thorium emitted similar radiation. Most importantly, the strength of the radiation depended solely on the element's quantity and was not affected by physical or chemical changes. This led her to conclude that radiation was coming from something fundamental within the atoms of each element. The idea was radical and helped to disprove the long-standing model of atoms as indivisible objects. Next, by focusing on a super-radioactive ore called pitchblende, the Curies realized that uranium alone couldn't be creating all the radiation. So, were there other radioactive elements that might be responsible? In 1898, they reported 2 new elements: polonium, named for Marie's native Poland, and radium, the Latin word for ray. They also coined the term radioactivity along the way. By 1902, the Curies had extracted 1/10 of a gram of pure radium chloride salt from several tons of pitchblende, an incredible feat at the time. Later that year, Pierre Curie and Henri Becquerel were nominated for the Nobel Prize in Physics, but Marie was overlooked. Pierre took a stand in support of his wife's well-earned recognition. And so both of the Curies and Becquerel shared the 1903 Nobel Prize, making Marie Curie the first female Nobel laureate. Well-funded and well-respected, the Curies were on a roll. But tragedy struck in 1906 when Pierre was crushed by a horse-drawn cart as he crossed a busy intersection. Marie, devastated, immersed herself in her research and took over Pierre's teaching position at the Sorbonne, becoming the school's first female professor. Her solo work was fruitful. In 1911, she won yet another Nobel, this time in chemistry for her earlier discovery of radium and polonium, and her extraction and analysis of pure radium and its compounds. This made her the first, and to this date only, person to win Nobel Prizes in 2 different sciences. Professor Curie put her discoveries to work, changing the landscape of medical research and treatments. She opened mobile radiology units during World War I and investigated radiation's effects on tumors. However, these benefits to humanity may have come at a high personal cost. Curie died in 1934 of a bone marrow disease, which many today think was caused by her radiation exposure. Marie Curie's revolutionary research laid the groundwork for our understanding of physics and chemistry, blazing trails in oncology, technology, medicine, and nuclear physics, to name a few. For good or ill, her discoveries in radiation launched a new era, unearthing some of science's greatest secrets.
To wrap up this first section, let's look at the penetrating ability for the different alpha, beta, and gamma radiation particles. Alpha particles can be stopped by paper. Beta particles require at least a centimeter of lead, and gamma particles require at least 10 centimeters of lead. So if we look at the energy of those 3 radiation particles, gamma is the greatest, and then beta, and then alpha. The penetrating ability of these 3 is the energy associated with the radiation that's transferred to the material. This fact is important because the damage caused by radiation is related to the energy absorbed.